C equals Q over M delta T. We were talking about, when we very carefully discussed the relationship between C sub P and C sub V, we were talking about the specific heats of I think we stuck to a monatomic ideal gas, either in a constant volume or a constant pressure process. And now, as a more broadened statement, let's talk about other objects, not just gases, but let's talk about maybe solid surfaces, like a block of metal. Then it has a specific heat, which experimentally you can determine very easily by put a known quantity of heat into this mass of material and measure the temperature change caused thereby. And you have the specific heat of the material. As you recall, knowing specific heats, for example, can help you minimize. Let's say you have an unknown sample of material. By measuring its specific heat, you can get a reasonable idea, or at least minimize the number of possible choices. Specific heat is unique. It's a unique property to the material. And so in material science laboratories and so on, they're doing these kinds of experiments all the time. Perhaps we should say, a little bit differently, we should say Q equals MC delta T. If you wanted to change the temperature a certain amount on this mass of material, all you have to do is know the specific heat. You can calculate the heat flow necessary for that experiment. So Q equals MC delta is a very common statement. I'm sure you've seen it in the chemistry lab. And it simply relates this measurement, C, the specific heat of the material, to the experiment itself. Well, that's all well and good until you try to do an experiment like this. Let's imagine that we take ice. This will be Q. This will be T. Let's say we take ice, water ice, at standard conditions, that is atmospheric pressure. And we're going to start out with it perhaps at low as degrees C and joules here. Perhaps as low as minus 10 or minus 20 degrees. And of course, we've got this block of ice. You add a little bit of heat, the temperature goes up. You add some more heat, the temperature goes up. Just like you would expect. Let's use a red. We're adding heat and the temperature is going up very dramatically up to a certain point. At that point, of course, 0 degrees. Now you add some heat to the ice and the temperature does not change. You add a considerable amount of heat to the ice and the temperature does not change. But what does? That's correct, the change of state. It goes from a solid to a liquid. So as you slowly put energy in, the ice changes to liquid water without changing temperature. After you have melted all of the ice, now it goes back to behaving properly. Now you've got water at 0 degrees C, add a little bit more heat, and sure enough, the temperature goes up. And that happens again until another measured temperature, which is 100 degrees C. So over here is 100 degrees. And then again, as the water changes phase from liquid to gas, you add heat, but there is no temperature change. So when you're gasifying the water, it takes a considerable amount of heat until all of the liquid has turned to steam. And then finally, at that stage, when you add even more heat, the temperature goes up again. Like this. So there's two interesting areas here and here, change of phase. Also implied, I hope it's obvious from the way I drew it, it's also, I think, obvious in any graph that you look at, that the slope here and here is more extreme than the slope here. What does that suggest to you? The specific heats are different here and here. When you have a certain amount of heat flow in this region, you get a more extreme temperature change. Likewise here, a certain heat flow in this region, you get an extreme temperature change. Whereas over here, you put in a certain amount of heat and you get a temperature change, but not as extreme. What does that tell you about the specific heat? Well, if the specific heat is large, the temperature change will be small, and vice versa. Hence, therefore, the specific heat of water, when it's a liquid, is going to be a number which is different than the specific heat of steam and ice. Furthermore, let's talk about the latent heat now. This area here, the heat that flows does not change temperature, so we have to have a different formula and say for the heat that flows, there is simply the mass is changing into, the latent heat of fusion, is changing its state, or Q for fusion, Q for vaporization, mass times the latent heat of vaporization. So there's no temperature change. That's why we call it a latent heat or a hidden heat. There's how we describe it. Now, having said those simple things, we've got a specific heat and a temperature change here. We have a latent heat here. We have a specific heat, temperature change, a latent heat, specific heat, temperature change. Let's now just set up. Let's take a moment. Maybe we should have table competitions. Let's take a moment. You guys at the tables, describe to me the, I guess we can get a bottom line answer. How much heat? How much heat? Ice at minus 15 degrees Celsius to steam at 110 degrees Celsius. How much heat to go from, ice at minus 15 degrees C to steam at 110 degrees C?
Do we need to know the quantity of it, or do you want to just leave the quantity right now?
Well, we're going to need a quantity, yes. And let's choose, I don't know, 2 kilograms. 2 kilograms of ice. And I found the page, it's on my notes, but I don't even find my notes in front of me now. I hope every table has a textbook. If not, I'll open my textbook. In chapter 20 on page 682. So, what did we say? Mass equals 2 kilograms, and see page 682. Okay? Let's take just a couple of minutes, and most important thing is the strategy, not the final answer. In a minute, I'm going to start putting the strategy on the board, but I'm going to do it quietly. Please do not look up until you think you have it right.
They give it to us in kilograms. Ice is 206. About stew. I wish I forgot more.
Ice, melt it, not vaporize it. Melt it, vaporize it here, and then warm the steam. Of course, it's all the same mass, so we factored that out. And now we have to go look up numbers. I was running back and forth to my book over there, but the specific heat of ice is 2060. Of course, the temperature change is 15 degrees. Well, it's 15 degrees Celsius, but it's also 15 degrees Kelvin at the same size temperature measurement. So the water, excuse me, so here we melted the ice, and we have the specific heat of ice and the temperature change. There we have the latent heat of fusion for ice. Then we have the specific heat of water, which is different. You'll notice that it's virtually twice as big, from 2,000 to 4,000 joules per kg Kelvin. And we have a temperature change of 100 Kelvin, obviously, because we're just warming the water up to the vaporization point. Then we go look up ice. The specific heat of ice, the specific heat of steam is very similar to the specific heat of ice, and again, about half of what water is. That's about 4,000, this is about 2,000. And we warmed it up 10 more degrees, didn't we? Yeah, it went up 10 more degrees. So the only minor little thing I'd like to point out to you, when we're all done working out the units, and I'm kind of fond of using different colors, kilograms, there's a kilograms in common downstairs, inside everywhere. On most of the terms, there's a kelvins up here and a kelvins down there, leaving behind joules, but this number is in kilojoules. Joules again, and this number is in kilojoules, and joules again. So that's the only thing you have to be cautious of. You need to, in place of this, of course, this number has to be written as 334.7 times 10 to the third joules. And likewise, 2272 10 to the third joules. And then we're really ready to calculate. We can simply add, do these multiplications, 1, 2, 3 multiplications, and then add everything together and multiply times 2. I didn't bother to work out the number because I'm sure you guys can work the number out if you need to. I did want to point out, I think the main reason for doing this, well, there's two things, but the main reason for pointing this out is, number one, you should say to yourself what's going to happen. Warm the ice, melt the ice, warm the water, vaporize the water, warm the steam. I said 5 things, there should be 5 terms. And be careful because the latent heats are given as kilojoules, whereas everything else is given as joules. Christine?
Does the specific heat depend on temperature?
Actually, yes, it does, but we're not going to take into account the specific details of the specific heats. We're just going to take these things, for example, like this number right here. Oops, where is it? This number here, or here, or here, as the averaging unit.
0 degrees specific.
We're going to assume it stays constant because it changes so very little.
So we have to put that.
You don't have to put that down. Just put it down as because it comes out of the book that way as a number in the table. All right. So specific heats. Am I correct? You've seen something like this in your chemistry class? Okay. Good. All right. So our textbook has some nice charts in it that are very, very helpful. Next topic in the same chapter on the thermal